name is Timothy Beers. I'm a University Distinguished Professor of Astronomy here at Michigan State. I study the formation and evolution of the very earliest stars in the universe, which is a challenge because the real first stars to have come out to emerge shortly after the Big Bang were in fact very massive, lived short lives, and exploded. So they're gone. We're never going to find those again. At least there's no reason to expect we'll see them again. But what I find and what I work on are ways to find the low-mass stars which formed shortly after those objects, because those low-mass stars have remembered in their atmospheres the elemental abundances produced by the first stars. So indeed, my major activity is to find indirect evidence for what happened first. The research I do, not only through the astronomical observing, but through the interpretation that comes with it, is trying to tell a story of how the elements were formed. There are many different mechanisms that we know from fundamental nuclear physics that tell us that there are a variety of pathways that elements heavier than hydrogen and helium could have formed. And what I try to do is to find the astronomical evidence that allow us to actually separate out what were the most important processes at what time and in what environment they actually did this. Now, the question often arises, why does this matter to physicists? It matters just like any other fundamental research question. You want to tell the story. Ultimately, we are the endpoint in today's universe of this whole story, but we'd like to tell it from the very beginning all the way through to now. And the murkiest part of the story is right at the beginning. In 2001, a group that I was working with, primarily based in Europe, led by Roger Querelle of the Meudon Observatory in Paris, we actually were taking very high-resolution spectra on one of the world's largest telescopes, something called the VLT. It's 4 8-meter telescopes in South America. We were doing follow-up high-resolution spectroscopy of a list of stars that I and my group had discovered many years before, hoping to measure individual elements and abundances of those elements in those stars. One of the stars, it turned out, showed a very strong signature of what nuclear astrophysics people call the R-process elements. These are elements such as europium, hafnium, holmium, thulium, all those hard-to-remember elements on the end of the periodic table. But included in that laundry list was both thorium and uranium. And this star was the very first one in which uranium, other than the sun, we'd see uranium in the sun, the very first one in which uranium was detected. And the important thing is, because uranium has an isotope which is radioactive, U-238, that actually provides a sort of clock that we can use to tell us how long it has been ticking. And the same applies to thorium with a different half-life. And so when I explain this to people, I use the analogy, it's like walking into a room and you see 2 clocks in the wall showing different times, but you study them and you notice they're ticking at different rates. And if you measure the rate that they're ticking, in principle, you could run that experiment backwards to ask when, in real time, did they begin ticking. Bring them back to midnight. And indeed, this is essentially what we do when we look at the abundance of uranium and thorium. Michigan State is a university partner in a 4.1-meter telescope which sits on a mountain called Cerro Pachon in Chile, South America. And that has been a real revolution in the kind of telescope access that we as faculty and especially the students have here at Michigan State University, because we can control this and interact directly with it without going to Chile. We have a remote observing center in the first floor of the BPS building, and typically probably 30 to 40 nights a year there are faculty and students observing in Chile from that observing center. And what that allows me to do is to give my graduate student instructions and train them, of course, as to what observations have to be made, and then they'll take care of it. I don't have to be staying up all night. I don't have to travel to Chile. I don't have to get people to take my class the next day. That can all be managed. And in the past, most students would never have the opportunity to travel half around the world to conduct observations, so they didn't do them. But with the SOAR telescope here on campus, we have big science being done here at MSU, giving people the experience and the training they need for later in their career. The connection between observational astronomy and what gets done at accelerated facilities is actually an intimate one, because as many people are aware, at accelerators they are ultimately trying to study the fundamental masses, fundamental interactions, fundamental measurements of individual nuclei, which we know are involved in these processes that build up heavier and heavier nuclei. Students today are in an interesting position because certainly observational astronomy is in a transition, and it involves the technology, as you might imagine, but also it involves techniques. And what I mean by that is, in my day, I would get an idea, I would try to get some time on a telescope and try to demonstrate that this might be useful. Maybe I'll get more time, maybe I'll get some grant support to do that. But that overall is a very slow way to proceed. And the pace of the research has picked up so much more that really the only way forward, and exactly the pathway which is being followed, is to go to these massive surveys, such as the Sloan Digital Sky Survey, and many more to follow, which indeed will present us with the raw information that many people can use and look at, instead of one person at a time.
NSCL is a world-leading laboratory for rare